All right, thank you, Helena. Next up is Peter Hoos from Facebook to tell us about managing, deploying, and operating large-scale networks.
Hello? Much better. All right. April 13th, 1970. Can you hear me? Yes. April 13th, 1970. A routine procedure turned tragic. As Apollo 13 approached lunar orbit and they began a cryostar, tragedy unfolded. An explosion occurred, and the lunar module was badly damaged. They were unable to complete their mission. As these astronauts were faced with this challenge, one thing was clear, was they were going to get back to Earth. Failure was not an option. Now, you might be asking what this has to do with network engineering. And the truth is, how many of you have been in this room, have ever been in a NOC, or been on call when a network failure has occurred? Raise your hands. Okay, like a few of you. For those of you who have, how many of you have dealt with a compounding failure? A major network outage caused by a fiber cut, followed by a device failing, followed by a bad push, followed by something else occurring causing major outages. Well, I know I have. And in these scenarios, it kind of feels like you're in mission control, right? You're surrounded by the best and brightest, all focused on a singular problem, trying to resolve it together. And in these scenarios, I think there's actually a lot we can learn from NASA, and a lot we can apply from the Apollo missions to managing a large-scale network. And the first of those is that we must be willing to take risks. Without risks, we can't make progress. We can't move forward. Without risks, there would never have been that one small step for man. And the second is we have to be willing to embrace hacks. In the case of Apollo 13, as they were coming back to Earth, it was clear they didn't have enough oxygen to survive. They were able to use a clever hack to adapt components from the command module to work in the lunar module to bring them oxygen. And they did this using, and I kid you not, duct tape. Duct tape, the solution to all of man's problems, and the thing that saved these astronauts' lives. It's critically important. The last lesson that we can take from this is to embrace automation, to leverage it. Even in the 1950s and 60s, when computers the size of a room were no more powerful than the cell phone in your pocket today, NASA saw the power of these. They were able to calculate trajectories faster, more accurately, and with greater frequency than would have been possible with humans alone. So let's apply this to networking. 2011, a good-looking engineer got up here on stage at NANOG and complained about troubleshooting and managing large-scale networks. That engineer was me, and the talk was entitled One Engineer's Rant. This talk can be considered somewhat of a follow-up to that. The tools at the time were rudimentary. They failed a lot. They didn't work. The data we had was basic. This talk is entitled Solutions, Lessons Learned, and What Not to Do. Hopefully, we can take what we've learned from NASA, and as well as what we've learned in running a large-scale network for the last couple of years, and help to make these better. Now, this isn't the work of just one person. This takes a team of highly talented people. And I'm just the one up here presenting it. But these people, the names here, are some of the people who worked on the projects you're about to hear about. So let's get started. And first, let's address some myths. The first is that automation fixes everything. It doesn't. It's a tool. It's an add-on. It's an augment. It's like saying eyeglasses replace a human. They don't. They simply make your vision better. They make it stronger. They make it better. This is very similar for automation and networking. It doesn't replace the human. It just makes them more powerful. The second is that the large networks out there have fixed everything. Google, Microsoft, Facebook, Amazon. We haven't. When I look out on the future, there's more left to be done than has already been resolved. And the last is that this doesn't apply to you. Maybe you have a small network, or a small team, or just 2 or 3 engineers. You don't need automation to make these things better. Hopefully by the end of this, I'll have convinced you otherwise. So let's take a look at some examples from where we've used these tools to make our lives better. Microbursts. Raise your hand if you've heard of them. Almost everyone. Raise your hand if you've ever had an outage or issue caused by microbursts. All right, now keep your hands up if you were able to conclusively identify the source of those microbursts, track down the cause of them, and ultimately, I see Jimmy, come to a final resolution and root cause solution for that problem. Almost nobody, like one dude over there. Congratulations. This is a tough problem. This challenged us for quite some time, and it started with the service owner reporting issues. They saw loss in some of our new deployments. They saw things like TCP retransmits and resets increasing. Like any good network engineer, we dug into the information we had. This is things like interface statistics. Okay, it's up, hasn't flapped in a while, no capacity problems, no errors. We checked our protocol states, our syslog, all the data we have available. There was no indication of a problem. Move on, right? Not a network issue. Except we could recreate it. And it was significant. This thing was causing a massive amount of packet loss. So we did what we had to do. We dug in deeper. We looked for commands that we hadn't known about in the past. We dug deep into the hardware platform. We looked for data that was not exported externally, not available via SNMP or XML or anything else that might show us a problem. And what we found was an ASIC drop indicator that happened to increment when this problem occurred. So when we took that information and we overlaid it with the physical topology of our network at the time, where each blue square indicates a rack, we could see that this problem only affected a subset of racks. And all of those racks ran a single service. This was actually good news, because this meant we had an idea what the problem was, microbursts. We had a counter that told us it was occurring. And finally, we had a culprit, a suspect in hand. But where to go from here? In a typical network engineering case, we might get stuck. It's hard to go from this point. What do we provide the service owner with to tell them that they have a problem and where it is? Well, this is where the magic of software comes in. Magical. Because of the sparkles. In this scenario, we crafted a bit of Python to run on our servers to collect statistics at high rates. Every 10 milliseconds, we recorded the throughput, and we did this for 5 minutes. Now, the problem is this was kind of CPU intensive. It was kind of sketchy. We were network engineers. We didn't have any business writing code that ran on our servers. Needless to say, we were afraid to deploy this to the hundreds of thousands of servers that ran our site. So instead, we crafted a bit of Perl. We used this to analyze the devices themselves, to look for when these ASIC drop encounters were occurring, to isolate it down to the location where it was happening, and then allowing us to run this Python collection in a more targeted fashion on the subset of servers having the problem at that time. And the result was cool. It turned out we were having a microburst problem. It turns out there were spikes to full line rate in a sub-second time period. And this would happen on multiple devices at the same time. And if enough of these did this in parallel, we could consume the full 10 gigs available to that ASIC. This indicated why we were having these problems, it proved that we were having these problems, and it clearly explained why the 30-second average counter on the interface didn't tell us. It had smoothed this out. So we took this information and we met with the service owners. We told them what we were seeing, we provided the data, and we sat down and said, how could this happen? What's causing this issue? And what they discovered was that their application was using memcache. And memcache had implemented a windowing mechanism similar to that of TCP's. This controlled the amount of parallel flights that could be in flight at any time. And if we tuned this, possibly we could fix this microbursting issue. And the result of those tests, where we tried different parameters and different configurations, was this graph. Pretty straightforward, so I'm not going to explain it. Everybody got it, right? OK. It took a little while, but once I explain it, it'll make sense. On the y-axis, you have throughput in megabits per second. Across the x-axis, you see a count, the number of times we recorded a measurement at that throughput during a 5-minute test. And finally, you have the colored columns. Each of these represents a test with a given memcache configuration. Once you know this, it's pretty clear to see what's happening here. This light blue column is very bursty. There's a lot of measurements above 500, 600, 800 megabits per second. While the left-hand column, the dark blue column, that one's not so bursty. It's actually ideal for the network, very few bursts. The downside was this actually incurred latency and negative service impact on the service itself. So the end result is we ended up with something like the purple, a good compromise. Not too much network impact, not too much service impact. So this resolved our problem. We changed these settings, the microbursts went away, we were happy. Now after any major event in our network or in our infrastructure, we sit down and we look at what went wrong and what we could have done better. And what we found were some interesting things. The first, we resolved the issues. Easy, that was awesome. Second, we determined the root cause, also a really good thing. Now we were sure this would never come back. And lastly, we learned something fundamental, that we could use software to better troubleshoot, triage, and manage our networks. With these tools, we could solve problems that we weren't able to solve before, and we can do it pretty quickly. But there were some things that didn't go as well, too. The first is a service owner had to tell us the network was broken. That's pretty backwards. As network engineers, we should be the first to know that there's a problem. We should be telling them that there's an issue, and we should be reacting. But that wasn't the case. The second is this took a long time to resolve. I talked through it in like 2 to 3 minutes here. This played out over weeks and months, and each time the impact was significant. And the last one, and one we didn't understand at the time, was that even small amounts of loss can cause really significant impact to our service. Let's look at another example. Link imbalance. Okay, if you've ever had more than one router connected to more than another router with more than one path, raise your hand. I'm interested in the people who didn't raise their hands. Hopefully this is pretty common to you. In a lot of these scenarios, you have these multiple paths, and you expect them to balance traffic relatively evenly. Maybe not 50-50 or 25-25-25, but give or take a few percent. Well, let's look at an example. We have 2 routers with 4 paths between them. We'd expect traffic to be divided, roughly 25% of the utilization hitting each link. And this worked most of the time, except when it didn't. We had this one link that, for unknown reasons, just spiked to 100% utilization. The other links, they kept doing what they're supposed to do. They operated normally. What was going on here? That's what I was thinking. Well, as we dug into the data, we learned a lot of interesting things. And we tried a few things, and we tried some very sciencey approaches to this. And the first bit of science we applied was just shut the link down. Maybe the problem goes away. Science. The good news is it worked. We solved the problem. All we needed to do is call our vendor and tell them there's some weird bug and they needed to fix it. Except it didn't really work. The problem came back. And unfortunately for us, where we'd expect this to move to a different pair of links or a different link on the same chassis, it didn't. It moved to a completely unrelated pair of devices. Now I'm going to stop here for a second, because those of you with more experience and more background in this networking thing might say, hey, this is a classic fat flow issue. Check your flow data, and what you're going to see is that one flow has magically appeared during this time and is pegging that link. And I'll tell you what I told our vendor, ever so eloquently, gently, and politically correct at the time. After many months of digging into this problem, and them suggesting this solution over and over and over, that it's a fat flow, I simply told them, it's not a fat flow. I might have followed that with, if anyone else says that, they can leave the room. How did I know this? Or how did we know this? Well, we looked at the data. We had a lot of good flow data. And there were some really interesting patterns in it. In fact, the most interesting pattern in the flow data was there was no interesting patterns in the flow data. Before, during, and after the event, it looked exactly the same. There was no fat flow. The second is when we looked deep at that interface utilization graph, it turns out that the other links, the ones that were seemingly unaffected, they actually reduced in traffic. Now, a fat flow could explain one link pegging, but it wouldn't explain these going down. In fact, what appeared to be happening was traffic was leaving these links and migrating to the other. No fat flow could do that. This didn't make any sense. We also didn't really have any good solutions for this. In fact, the only thing we could do to solve this was effectively play whack-a-mole. Shut down links, line cards, and devices and hope and get lucky when the problem went away. Or we could just wait. Eventually, traffic would go down, the links would resolve themselves, and the problem was gone. This was great, it worked, but probably not the best solution possible. This graph was over the course of several hours. All that time we're dropping bits, all that time we're affecting our users. Which got us thinking, what's going on here? So let's look at what we did know. This only affected our backbone devices. It typically only affected links that had greater than 80% utilization, and it was migratory, such that if you shut down one link, it would move to another link or another device. Clearly, we had a vendor bug. So we sat down with our vendor, and we looked at their ECMP algorithms. We dove deep, and we found a couple scenarios where maybe 1 in a million or 1 in a billion cases, this could actually cause some imbalance. And we worked with them on a fix, and we deployed it. Maybe Facebook's unique enough. Maybe our traffic's weird enough. Maybe 1 in a million for us is every week or every month. This would be great, right? Deploy it. So we rolled it to one device, no problems. We rolled it to the fleet, no problems. And then it came back. So we sat down again. We found some more 1 in a million scenarios. We rolled it to a device. We rolled it to the fleet. And guess what? It came back. Nobody guessed that. It was kind of obvious. The problem kept coming back. And the problem was we did this over and over and over the course of several months. We repeated this process where we got new code and rolled it out to our devices, only to be met with the same problem again. Until one engineer, in a bit of frustration, came up with a pretty novel and simple solution. It turns out your egress port is determined on ingress by looking at a series of parameters, things like your source and destination ports, your destination IPs, source IP, as well as a random seed or hash. If we could just take that random seed or hash and change it when we detect this problem, we could resolve the issue. Here, you can see a couple of links, more ingress flows hitting a single path. Roll the hash, problem's gone. This worked. It worked really well. In fact, it basically completely solved the problem. Until it didn't. The problem came back. And this time it wasn't in our backbone, it was in our data center. Our data center runs different vendors, multiple different vendors, with different hardware, with different configurations, with different topology and different protocols. In fact, there's almost nothing the same with our backbone. The only common thing here was our application. So what were we going to do to fix this? We still didn't even know what it was. Well, the good news is, in that preceding time, is we learned how to write software. We learned how to use it to make our networks better. We learned how to use it to address our problems in real time. So we asked ourselves, can we use some of these tools to resolve this? Well, we built a detector. This would tell us when the problem was occurring so that we knew first. And when that detector fired, we could call a system called FBAR. FBAR is our automated remediation engine. And it sounds complicated and insane. It's really just a cron job on steroids. And this system could then log into our routers and run a CLI command to roll the hash for us. And guess what? It fixed the problem. This was our duct tape. This kept us alive, and this saved our network. Just this little hack. You might ask yourself, why not just hit those vendors up and ask them for the same patch you had from the other? Well, a couple of reasons. One, that took months of trial and error to get it right. Two, that would then mean that any new vendor that entered our network would have to have that patch before we could even test it. That was unacceptable to us. Problem is, it came back. It would be comical at this point if it wasn't so painful. And this time when it came back, it was in a more edge case. Some of our older layer 2 clusters, or devices where we didn't have the CLI command to roll the hash. So what we did now is with the cover of this hack and these patches, since this only happened very rarely now, we sat down and did another war room. We sat down with 10 or so engineers, and we focused on the problem. We came up with the data we wanted to look at and some theories of what we expected to see. We looked at TCP retransmits and resets, and we expected these to increase. And they did. And then we looked at TCP receive window, and we'd expect this to decrease, because that's what TCP does in the face of congestion and loss. It backs off. Except in this case, it didn't. In fact, it actually increased. In other words, in the face of loss and congestion, TCP tried harder. TCP tried harder. It didn't back off. Like one person laughs. As we dug into this further, we looked at the open connections graph, and we saw another interesting piece of data. Now again, we'd expect this to stay flat or decrease, and it didn't. It increased, and it increased dramatically. And the smoking gun here was that it fell off dramatically right as the problem would resolve. So now we had a pretty good idea that this was the smoking gun. This meant something. So we took a look at the data, and we realized that almost all of these connections existed between just two services in our network, Tau and database. Tau is another caching layer at Facebook. When we sat down with these engineers, we asked them how it worked. What could possibly cause this kind of issue? Well, it turns out Tau opens multiple parallel connections to our database. And it does this for performance reasons, to avoid opening and closing connections all the time, and to get more throughput when things slow down. It also implements a most recently used connection policy. And what this means is the last connection that had a reply on it is the one that's going to have a new request sent upon it. Great idea, except when there's congestion. As these packets take time to come back, guess which packet was the most recently received? The slow one, the one on the congested link. So what does Tau do? It replies down that slow link. Eventually, it pegs the link, and it does this over and over and over and pushes harder and harder and harder. This explained our problem exactly. This was traffic moving from one link to the other because it was taking connections that already existed and moving traffic onto them, off of them, onto others. This was it. We were only left with one problem: how to fix it. Well, it turns out it was pretty easy. It was like 50 lines of code in Tau and the problem was gone. Now we needed one more thing. We had to prove that this was resolved. How could we do that? Well, we can test it in prod. In fact, we had to test this in production. It was the only way we could be absolutely sure that the problem was resolved. Now, what we found was before every one of these events, there was usually a congestion event, a device crashing, a line card going offline, or major file transfer. So what we needed to do was inject congestion into our network and see what happens. We did that in a very scientific way. We took a network with 4 hosts in it, 4 routers, and we shut 2 of them down. We literally caused a major catastrophic failure that was larger than we'd expect, caused major packet loss and a major impact to our site to recreate this event. After what seemed like 2 to 3 days, but was really like 10 seconds, we turned those boxes back on. We crossed our fingers, and we hoped for this imbalance to occur, and it did. It came back. We switched the algorithm in Tau to the new one. Problem was gone. This was literally one of the most exciting points in my entire career as a network engineer. We'd been chasing this thing down for years, and it was resolved at the flip of a switch. It was amazing. So we sat down afterwards and did the same kind of follow-up. What could we have done better, and what went wrong? Well, we had some good lessons. First, we resolved the issues. That was good. Second, we had a root cause. Also good. Third, we learned that software can really help us to manage our network in a different way than we could before. On the bad side, a service owner had to tell us about this. The time to resolve it was months, and actually years before it was finally resolved. And we learned again that small loss can cause insignificant impact. Now, if any of you remember my first slide where I talked about the lessons learned, clearly I didn't learn my lesson because these are the exact same things. We repeated all the same problems, we repeated all the same issues, we didn't move forward at all. So we now sat down and said, we're going to solve this. The first thing we had to resolve is the service owners telling us about a problem. As network engineers, we needed to know first. We had to know the network was broken. So we built a system that between 2 clusters would ping all the different nodes. Then it would record these results in a database, indicating things like loss and latency, report this back, and our system would look at it and say, okay, has this crossed a threshold? Is there more than N% loss or more than X% latency? If so, it would generate an alert. We started out rather conservative. We alerted at things like 5% loss, and we moved this down over time. Each time a major outage occurred, we said, did this system catch it? And if it didn't, we tuned it until it did. And slowly but surely, that 5% moved down and down and down. Until it got so low that we said, maybe we should test this. Maybe we should figure out what the lower bound of this actually is. Can anyone guess what the acceptable amount of continuous packet loss is for TCP? Not much. It's probably less than you'd think. Even in an optimum scenario, that with basically a zero RTT, even as little as 0.1% loss can cause as much as a 50% reduction in throughput. It only gets worse as RTT goes up. In fact, as you approach 25 and 200 milliseconds, that same 50% reduction happens at 0.0001% loss. In other words, there's no acceptable amount of continuous loss. And the reason for that is actually simple in hindsight. It's because TCP, when faced with loss, sees it as congestion. And it does what TCP is supposed to do. It backs off. It goes slower, and it does this very aggressively. Next, we wanted to see if there was a difference between algorithms. So we tested Reno, Cubic, Vegas, and Illinois. And the answer is there's a pretty significant difference. In fact, between the worst performer, Vegas, and the best performer, Illinois, there was as much as a 4x difference. Vegas was operating at 50 megabits per second, while Illinois was operating at nearly 200 megabits per second. This is significant. The next thing we did was we looked at how fast they could recover from a failure. Now what's interesting is, literally as we were doing this, our database team came to us and reported that they basically could not recover from failures. After a large fiber cut or a device died, the database tier would take a long time to ramp back up to full speed. In fact, their solution was just to kill all the connections and remake them so that it would come back at a higher speed. But we wanted to understand why. So we injected 1% packet loss for 30 seconds. And then we unleashed these different algorithms. And the difference was staggering. The difference between the best performer, in this case Cubic, and the worst performer, in this case Reno, was nearly 15x. Basically, after 2 minutes, Reno didn't really recover at all, while in 20 seconds, Cubic was back up to full speed. And what was interesting for us is that we learned by accident, for some historical reasons, that we actually had Reno deployed in a lot of places in our network. We then standardized across the fleet and deployed Cubic everywhere, all as a result of this. So this should leave you with a question. Earlier in the talk, I said this could apply to you. And then I went to talk about an esoteric, weird situation of microbursts, a really specific link imbalance issue that can only affect us, and finally, these TCP problems that, again, are pretty specific to a large-scale network. So how does this apply to you? Let's look at a more practical example. In parallel, while we were doing this, we also started getting really good at alerting for things. In fact, we got so good that we had an alert for basically everything. The problem was, we had an alert for basically everything. We ended up with like 70,000 active alerts, and we only had 5 engineers to attempt to resolve them. This just wasn't going to scale. We had to do something about it. So we said, can we use software? Can we use these tools to make this better? The first issue we went after was basic interface issues. Anyone want to guess why? Targeted opportunity. Well, because in the last slides, we just learned that small amounts of loss are really significant. Interface issues often cause small amounts of loss, 1%, 2%, 3%. They often also happen very frequently. And it turns out they're really easy to resolve. It's very straightforward. Everyone knows what to do with a bad interface. You check a few things, and you resolve it. Maybe we could take the power of our tools and apply it to this problem. And that's what we did. Today, when we detect an interface issue, we send that issue to FBAR. FBAR then checks to make sure that everything is OK on the peer device or peer interface, capacity, health, errors, so forth. It gracefully removes traffic from the offending link. It updates our database to let everyone know that this link has been pulled out of service. And finally, it places a call or opens a case to the engineers in the field to go investigate and resolve this physical issue. It solves the problem for us. This was huge. Those 70,000 alarms, we applied that same logic to all of our different problems. Line card failures, routing engine failures, power supply failures. And pretty soon, we went from 70,000 to today, we're closer to 100. We reduced that 70,000 by 99.99%. That is a major, major difference. And all of this was done without adding SLAs, without adding change control, without being mired in process, simply by writing small bits of software to resolve the issues we saw. To give you some perspective on just how much work FBAR does for us today in this system, in any given month, it processes about 3.37 billion syslog messages. Of those 3-some-odd billion messages, less than 1% actually become real problems. The rest are noise, false alarms, or correlated to other events. From there, FBAR interacts with our devices over 750,000 times every month. And in doing so, it resolves 99% plus of the problems entirely automatically without any involvement from us. To give you some perspective, if we wanted to hire people to do this, if we wanted to do the same thing with humans, let's assume that every one of those interactions, those 750,000, took 2 minutes, which is, I would say, pretty optimistic. It takes me longer than that to log into a router, but I type slow. If we convert that to hours, and we eventually convert this to man weeks, what you end up with is to solve the same problem, you need nearly 150 engineers to solve this issue. That's completely unacceptable. And on top of that, what did we learn from NASA? That these robots can do it faster, they can do it more consistently, and they can do it with greater frequency. And that's what we wanted to do. But on top of that, there was another benefit. They were also proactive. What happens when a fan tray dies in a large chassis? Nothing. Well, in many chassis, after 5-10 minutes, the device powers down. It goes into a protect itself mode. It makes sure it doesn't overheat. Now, I don't know about you, but when my $1 million chassis is overheating because a $2 fan died, I don't want it to just power itself down. Instead, I want to gracefully remove traffic. And that's what this system allows us to do. Today, when that $2 fan dies, we detect it, FBAR logs in, gracefully diverts traffic, and brings the device offline. It solved the problem for us. On top of that, if this happens at 3 in the morning, nobody's woken up. But I think there's also a more fundamental issue than just ROI, just doing things faster, just doing things better. And that's that the internet today is a critical part of our lives. And I said at the beginning that the difference between returning these astronauts to Earth and running a stable network, that the stakes were different. And it's true. But the internet's also critically important. When the earthquake struck Nepal, millions of users got online in a very short period of time. They let their families know that they were safe. They helped coordinate relief efforts. They helped to get donations coming in and helped to get things fixed. They helped to build their lives because of the internet. If we had 15-minute or 20-minute or 30-minute service degradations during this point, it would be completely unacceptable. In other words, failure for networks today is simply not an option. And with that, I'll take your questions. Thank you.
Ann Johnson. So you described this wonderful FBAR software. Would you care to say anything about the process that you used for determining whether an interface is actually down, for example? Because that's the magic. It's in your network. What defines a interface down, and also what defines what do you do about it in terms of where the traffic goes? And same for your other problems. And then as a follow-on, to what extent is what you've done at Facebook applicable to other people who don't have quite the same network infrastructure and self-built switches and so forth?
Sure. OK, so the first question there was how do we determine that this is a problem and what to do? The first is we get a ton of information from syslog. It'll tell you that an interface is flapping, going up and down, things like that. It tells you your state of BGP as well. We can also scrape the devices to get statistics on things like BGP state, OSPF state, and so on. And we can collect data from SNMP. We then build detectors that look at these stats and say, if a certain threshold is crossed, go do something. That tells FBAR to kick it off. In terms of what process to use, we just implement the software version of what a human does. So if an interface has detected problems, what does a human do? Well, we log into the router, we take a look at the statistics for it, we see if anything's violated, we see if they're reoccurring, and if so, we just take traffic off. In a lot of these cases, taking traffic off is as simple as just shutting it down. There's not much to do to divert traffic for an interface in an ECMP interface, just kill it. For a peering interface or an edge interface, it might be more complex, and those ones actually do have a lot more complex logic that is probably more specific to us tied around them. And I think the last part of your question was how can this apply to other networks, smaller networks? And I think the question is simple. Okay, so maybe not all of you have thousands or tens of thousands of devices, but how many of you have hundreds or thousands of cables in your network? 10% of the room? I feel like it's more than that. The answer in that case is that all of those links could be going bad. All of those could be causing major impact for your services, and all of those could be made more reliable and resolved faster with these kind of tools. Next question. How much time do I have?
In light of bufferbloat.net, in light of the microbursts issue and all your exploration of new TCPs, have you also been tracking the SCADFQ pacing stuff that's been going on?
I have not personally, but it's something I'd like to talk to you about if you think it can help. Sure. One more?
Alexander Lemon. The question is, you're threshold oriented, and moving the thresholds can be quite tiresome because today's anomaly, tomorrow's normal things. So who manages the thresholds? Do you have something in plans for something better than thresholds?
Yes and no. So the question being, do we have something better than thresholds? The first answer is we have other services inside of Facebook that alert on problems. There's humans occasionally who will look at graphs and things for weird anomalies. We also have general pattern detection in terms of like, this is different than yesterday. Not saying that, hey, today is 1%, tomorrow's 5%, just that this is statistically different than yesterday. And as a result of those things, we can take action as well. Does that answer your question?
How much time usually it takes for you to update your thresholds in daily operations?
It varies. If it's a very serious problem, a few minutes. If it's a less occurring problem or less frequently occurring, it's just a matter of time. That's probably one of the things that's not perfect, right? This does take people to kind of own it and maintain it and take a look at it and follow up. It's part of why we do these follow-up after major events is to say, did our system catch it? Did it react fast enough? If not, can we tune this better?
That answers the question. Thank you.
Thank you. And before I leave, hopefully you have one question left, which is how do I start? And the good news is it's a little easier than you think, maybe a lot easier. David Swafford tomorrow is going to be giving a tutorial called NetOps Coding 101. This will teach you, even if you have no prior coding experience, how to get started and build a system very similar to FBAR that you can use to automate your network. Hopefully, this is not just the end right here or with that. Hopefully, this kind of starts a movement or an interest in more people coding with network engineering skills. If you want to be a part of that, you can join this group on Facebook. You can post with the hashtag NetEngCode, and we'll follow you and learn about this and talk about this. We'll share as much as we can, and we'll try to teach you what we've learned along the way. And hopefully, we can build networks that are more reliable, more resilient, faster, and maybe, just maybe, keep some of you from getting paged in the middle of the night for routine issues. Thank you.